So this week we'll start laying out transistors and forming logic gates, starting with inverters at the very beginning. And so Tuesday, tomorrow, I think that's the inverter. So try to simulate, lay out and simulate inverter in electrical VLSI with LT-SPICE. And Friday we'll have a quiz. I was looking at all the topics that I can put on the quiz. These are just so many, so I don't know which one to pick up. I'll just pick up one of the topics. Can be the C5 layers. I'm going to go through the C5 layers for one more time today, just let you guys know how to draw the cross-sectional view of the IC circuits. And then we'll move to transistors, square law equations, and then inverters calculation. More about C5, the C5 layers. Seems to be pretty simple, but you still need to know what are they. And one of the students graduated 3 years ago, found a job in a company called XRF, a defense company making all these testing IC chips. So they design all the equipment to test the limits of the chips, of the silicon chips in the company, and they're selling this equipment to NASA, I think. And they are not expecting our alumni know the bottom layers of the transistor because they are testing the chips. Sometimes it's just the damage in the gates, but eventually the person who graduated from here, they knows all the details of the gates and diffusion in the silicon wafer, so which surprised them. So it's good to know this kind of details. You just never know, like at a moment in the industry or in the company, you just need that kind of knowledge to prepare you for the job. So first we just have to draw that Fox layer. Let's just draw it this way. I know if you look at all the different cartoons online or other drawings, they may draw a little bit more into the wafer. It's confusing. Let's just draw it. Just treat it as one layer on the top of the wafer. If this is a P-type sub or P-sub, P substrate, this is Fox, filled oxide. So if I have a layout like this, and this is metal 1, and this is metal 2, that's a VF, that's a M1 to M2 VF. Okay, I'll draw the cross-sectional view. If I draw a dashed line over here, just cut it from here, and then look from the side, and draw the cross-sectional view on the paper. It's metal 1, metal 2. So keep in mind that on the top of Fox, you got a 1 silicon dioxide, we just call it insulation layer, because you have so many insulation layers on the top. So they are all made by silicon dioxide as a pretty regular technology or process. It might be different, slightly different for the advanced technologies. And now let's just use silicon dioxide as an insulation layer on the top of the Fox. So Fox is a filled oxide, is also a silicon dioxide, but mixed with something else. And the first layer of silicon dioxide with the insulation hosts the gates. Since we don't have, do we have a gate here in this layout? We don't have a gate. So it's just the 2 metal layers. So the first insulation layer has a poly 1 and poly 2 layers, polysilicon. So polysilicon are being used for gate of the transistor. And poly 2, sometimes you have to use poly 2 as well in the C5 technology to form a cap. So what's happening is you have poly 1 and poly 2 in the same insulation layer, right? And have a metal trace. So this overlapped area is going to form a cap, right? So they're all in the first insulation layer, but we don't have a gate or any poly layer being drawn in the layout, so we don't have to draw anything over there. So on the top of it will be another insulation layer which hosts metal 1. So keep in mind the layer is not metal 1, the layer is insulation. You just have metal 1 inside that insulation layer. And of course, on the top of it will be metal 2. So how would you draw that cross-sectional view of this layout? Cross this line. This is the dashed line I cut from here. Like a pie, I cut it and then look from the side.
Do you want to make all of those layers, like the box and all that stuff too?
Because I cut it all the way down, right? So you'll be able to see this because all the transistors, all the metal layers are built on that same silicon wafer. What's the first one on the draw here? See because this is a cross-sectional view of the metal 1 first, right? So this is metal. So this is the metal 1's insulation layer. So here definitely will be a metal 1. Right? What's next? Draw metal 2. That's the width of metal 2, right? So you have a metal 2 here. What else? Draw the via. Okay, so the via connects metal 1 and metal 2. So the width of the via looks like this. So here will be the via. Make the connection between these two metal layers, right? Pretty simple, right? Okay. So in electric VLSI, the first lab, I believe you set up one parameter in preferences VLSI in preferences. There's a technology tab. This is fairly simple in electric VLSI. We just set up a lambda rule or lambda rule. Keep in mind we're using a lambda rule. It's a design rule for your layout. Lambda rule, which is 300 nanometers as one lambda. So we're using multiples of lambdas to space all the components or to design all the shapes of the components. So you'll see 1, 2, 3, 10, 20, 30 without any units in electric VLSI. So by default, you'll know that if you see a 1, it's 1 times 300 nanometers, which is 1 lambda. If you see a 10, it's 10 lambda. Okay, so we are using lambda rule to space all the components. And so there will be a lot of details of the lambda rule, but since you selected the lambda rule, which is 300 nanometer as 1 lambda in electric VLSI. So when you design all these, draw all these transistors and metal layers, if you move them too close to each other, it's going to report error. Remember? So like the wells and the metal traces, sometimes if you move them too close, you're going to see an error. And every time you move it, a lot of times it's probably moving by lambda, 1 lambda. So for example, metal 1 and a metal 1, right? So 2 metal 1 traces. Okay. And there might be a design rule for the space of the 2 traces, similar to the PCB design. Okay, the DRC rules. So you can set up the DRC rules in Eagle PCB. But in here, you don't set up the specific parameters. What you do is just use the lambda rule for it. So the space between M1, I think, is 1.5 is a minimum. So what's the minimum distance or space between the 2 metal layers? 2 metal 1 traces. 450 nanometers, right? Okay. And not just for metal 1, but also for the vias. If you have a via here, okay, that's a node, and here's a via, and you connect a metal 2 trace, and then you want to draw another metal 2 trace over here, and the distance between the metal 2 traces is also 1.2, 1.5. And the size of the via is exactly 1.5. Just the rule, okay? It's a square, 1.5. And overlap of via with metal 1 and metal 2 is a minimum of 0.5. 0.5. What does that mean? Overlap of via with metal 1 and metal 2 is a minimum of 0.5. I'm not getting that. It's okay. But as we know, the exact size of the via is 1.5 lambda. Okay. There are probably, just for the C5 layers, there are probably hundreds of different rules to define all the spacing and size of the traces. Nobody knows what are they. So you just use the EDA tools. Whenever you move them closer, you see an error. Then you keep them more apart away from each other. That's it. That's how to do it. Nobody knows. Nobody will remember all the rules. Okay. It's okay. So there's an example. For example, I have a bigger, pretty wide metal trace, like metal 2. And you got a metal 1. That's metal 2. That's metal 1. And here's a overlap, and here's a via. Okay. If the metal trace is pretty wide, but exact via size is 1.5, it looks pretty odd, right? You have a huge metal trace, but a little tiny dot in the middle, which is not really good design. So this will be optimized. So during your layout, if you draw a bigger metal 1 and metal 2 and you connect them together with a via, it's going to automatically generate multiple vias instead of just using one via. So the EDA tool is going to do that for you. You don't have to draw multiple vias by yourself. And the reason you prefer like more vias instead of just the one for the wide trace. You'll see this. The reason I want to bring this up is when you see this in your layout, you're not getting confused. Why I have many vias for one connection? So if you draw a model of it, if you model this guy into a resistor, so you have a metal 1 piece, metal 2 piece, and the resistor, which is a via, and metal 1 trace, right? So that's a via, for example. Okay, and for this case, you are having metal 2, and you are getting multiple parallel resistors instead of one resistor. So what's the advantage of doing this instead of doing this? Benefits. It lowers the resistance, redundancy. So during the microfabrication, if one via is broken, you still have other ones as a backup via, right? So to keep the connection. What else? You just got all the 3 points. So handle more currents, but also if you have the same circuit, it's actually lowering the currents. It's a current divider, right? You got parallel resistors is dividing the current. You got series of resistors is dividing the voltage. Okay. Lower the current. Make sense? And for the, this is easy. This one you need to know. The active layer opens up the Fox, keep in mind. Okay, I'm just repeating. The active layer opens up the Fox. You'll see active layer on the left-hand side of the electrical VSI, the design window. So you have a P-sub, and you used to have a Fox, uniform Fox layer, but if you have an active layer as a in your design file, okay, it's going to open it up. Exactly the same size because that's the design of the design file, right? That's the active layer. And the name of it could be N-act or P-act. You may still remember this term in which will be outside in the lab. Okay, it opens it up. If you need a diffusion, like dope the N material, N-type material into the silicon wafer, right? You need another layer, it's called N-select or P-select. N-select or P-select, which is going to dope the material into here. And these are Fox. It's okay to drop that material. You can see there's a little overlap between the select, N-select or P-select layer and the Fox layer. The reason I want to make the P-select or N-select layer slightly bigger than the window open up at the active layer is because you want to reduce a misalignment. It's just these are macro or nano level changes or a dimension. Right? If you make the same size, for example, you want to align this open as a window on the top of the opening exactly, there might be a little area will not be doped. You know what I mean? It's very difficult to align it exactly to the opening. So you would rather make it slightly bigger, start doping the material so it's going to a bigger window. So some of the material is going to drop onto the Fox, which is fine. It's just oxide layer. But I can make sure all the opening, the substrate in the opening is getting doped by the N+ material or P+ material. Okay. So you want to make the select layer is larger than the active layer is because you want to reduce misalignment. And now let's see how a gate is being doped to the substrate. So for example, this is a P substrate. It's Fox, silicon dioxide, or no, this is the poly layer in the silicon dioxide layer, in the insulation layer. I'm not drawing that insulation layer, but know that you can uniformly deposit the poly layer on the top of the Fox, right? And through that photolithography, remember last time, we are able to use a photoresist, right? And then use UV to etch the rest of the photoresist and then develop some layers or etch them out from the wafer. But eventually you can leave a little poly. A piece of poly can be a very short wire as a gate, but if you look from the cross-sectional view, it's just a little square on the top as a gate, okay? And definitely you can etch, you can remove the rest of the Fox layer as well, open it up to You use the active layer in order to dope a N plus or the diffusion into the P substrate. So here's the poly again, and that's a oxide, right? And the rest of the wafer is getting opened up by the active layer, and then you can dope to it. Okay, and eventually it's going to form a N plus on each side. So when you dope it, you put this in the vacuum chamber. So I got the chemical vapor inside the chamber, so it's going to fall on the poly as well, which doesn't matter because it's polysilicon and won't be doped by the diffusion material at all, but only the wafer will be doped. So if you look at this process, why we want to have the gate in that position first before we dope the N plus. So this is going to form a channel here, like NMOS, right? That's a transistor, basically.
You'll have to do the photoresist twice. The barrier to that center area to be each one.
Yeah, so think about what you eventually want, right? So you want a gate on top, and you need a diffusion at the bottom. That's the final product you desire, right? And they should be aligned. Okay, if you dope the diffusions to the wafer first, and then you want to put the polysilicon on the top as a gate. Again, these are nanometer dimension. How can I make sure you can put the polysilicon square directly on the top of the channel? Okay, just perfectly aligned without any like even 1 nanometer change. It's very difficult to align it. But if you have a gate on the top first, then you dope it, see? And this will become a perfect boundary between the channel and the diffusion. So poly, through this process, so the poly and N plus are self-aligned. Right? And if you look at the resistance for poly, sometimes it can be confusing because we use poly as resistors as well, but the resistance is low, so you need a longer distance or longer length in order to make up the same resistance. So poly's resistance is 200 ohms per square. Remember what's the resistance, the sheet resistance for the unwell? It's good to know this because when you are laying out transistors, or use a 3 metal layer technology to lay out complicated circuit, not really complicated, but you will find out it's sometimes difficult to route the traces, and you just want to make the poly layer longer, which is bad. For example, let's look at this one. Okay. Logic gates, right? See here. The pink one is a poly, right? Because that's a gate. The gate on the top of the diffusion, which defines the channel length horizontally. Okay, because the electrons are moving left to right. That's a VDD. And it's the metal one. Okay. So that's the polysilicon layer, which is the gate material. And after that, I directly have a via, the polysilicon to metal one via, right next to it. This one I cannot because I got a metal 1 here, so I cannot make this too close to it. There's a minimum distance between metals, metal 1s. Remember the design rules I just talked about? So if I move this node or via in here, this square, the space here is going to be too close to this metal 1. Okay? Did you get that? So I have to move it outside of this area to keep the certain distance between here and here. So you see the color, the gray color in the middle, it's not blue, but however, it is metal 1. It's just because it's on top of the pink, so it shows a gray color. Okay, but you should know that on the top of the poly layer should be metal 1.
So those two gates oriented like that would be basically when they're both activated.
Yeah, and the from AND gate, I'm going to show you why it's actually a wait, it's a NAND gate. It's not AND gate. A NOR gate, A NOR B. See, it's a NOR gate. Yeah. Yeah, you'll learn how that works later. But now we are just looking at the design rules of it. But you know, the reason that I know the via or the contact is a little contact between poly and metal 1, and I know that's metal 1. The gray color looks different from the blue colors, but I know it's metal 1 is because from the layer C5 layers, you know on top of poly is going to be metal 1. It doesn't make sense you have a poly and the contact is drilling the holes through 2 layers and connect to metal 2. You know what I mean? And you don't want to just to keep the poly in there without any contact, because you do need a signal to get into the poly or get out from the poly, right? That's a gate. It's a gate of the transistor. You need a signal to it. Make sense? So that's why in here I know it's metal 1. So this little contact is metal 1. The via is going to be the poly to metal 1 via, right? So that's why this guy cannot be too close to it. But however, if I have a metal 1, a poly to metal 2, I know there isn't that kind of thing. But if there's a poly to metal 2 contact, which means I can directly drill a hole from poly to metal 2, can I keep it close to the metal 1 trace? I know it doesn't exist, but if there is one, maybe in a different process, yeah, but not this one. Are getting my point here? Yeah, so what I mean is, so for example, where's poly in this drawing here? Do you know? Where's the poly layer? Below metal 1, right? So I got a poly layer here. Okay. If I have something like this, I can drill a via here, and then directly another via here, directly to metal 2. Can I keep this thing pretty close to metal 1? Because you still have the via in there. It's not routing to somewhere else, even though they're not in the same layer, but you still have a metal thing here, right? It's not metal 1, but it becomes a via. It's still a metal. Yeah, it's because it's a C5, it's a 500 nanometer technology. Based on the smallest node they can make on the wafer. The smallest node means pretty much the resolution of the technology, I think. So usually we.
Like, if you're going to smaller technology, you have to get smaller, but that doesn't. That's manufacturing technology, physical, not physics.
It just they define that kind of lambda to make it easier to calculate, I think. Yeah, but whenever the technology is smaller, I don't think they are still using lambdas. Lambda is a 50-year-old technology. They don't use that rule anymore. I mean, even for 180, they're not using this anymore. It's just thing it down to maybe a few numbers after the point, you know, instead of just using integer multiples of lambda. Mm-hmm. It might came from physics actually, the calculation. So you got that right. So the via is still a metal through that layer, so you cannot make it too close to each other, even though it's not a metal one, but it's still a via. It's still metal in that layer. Okay, so now you'll know why I have to keep this one here. I have to make this poly layer a little bit longer than this one. Okay, and this one can be short because there isn't any metal one around it. Okay, is this metal one? Is this metal one? Yes, because the transistor, this is the transistor, is at the bottom of the layer of the entire thing. Okay, and it's drilling holes to the top and connect all the diffusion, the N plus or P plus. This is a P plus. Drill the hole to metal one. That's the only layer. So from the diffusion, like this one, from here, these are the drains or sources of the transistor, right? You still have to drill a hole to the top and connect it to metal one or poly. Go up. Connect to where? Metal one. So you need the metal traces to be connected to the diffusions, right? The transistors, drain or source. Okay. So in that case, these are considered as metal one. So the via is a diffusion to metal one via. That's why I can use the blue color, which is metal one, to actually use that thing, use the metal one to draw a line to connect all the vias. Make sense? The via is having a contact with metal one. It depends on the length of the channel, right? I think the smallest the channel can make in the lambda in the C5 is 602 lambda, which is 600 nanometers. Even though the process it claims C5 is a 500 nanometer, like I said, you want to make it higher yield, better quality, so you make sure it's safe to guarantee the good quality. So you use just the 2 lambdas instead of exactly 500. Okay. All right. And why do I have to put a via on poly immediately, or just keep it in here instead of make a via somewhere else, then contact to metal one? Because you do need, so these are the input and output of the gates, like these ones, like these. Okay. I think this NOR gate has 2 inputs, one here, and this is the output. It's actually this one, and output. Okay. So these are just metal traces. You do need to inject or input signal to it to test the logic, right? It's a gate. You need an input, output. So 2 inputs and output. We're not designing a NOR gate right now, so we'll learn how to design it later. But now let's just look at the layout, right? So why do I want to put a via pretty close to the poly or the gate? Mm-mm. Why I don't want to make this longer, so it's easier to wire things up. You know, if I have this one here, I'm pretty sure if I have another gate next to it, so easier to wire things up, right? Why do I want? So this one I just have to, because this is what? What is this? Metal one. What is this? What is this? Okay, so I have metal ones in 3 corners over here. You want to keep this one too close, it's going to report a lot of errors. So this is pretty much the only space we can put in, you know, the closest to the gate here. But why do I want to keep it close to the gate? Resistance drops voltages, right? If I But metal 1, what's the resistance of metal 1? So sheet resistance for metal 1 in C5. So poly is 200, keep in mind, and metal 1 is only 0.1. It's a lot difference. So whenever you can use metal instead of poly to route signals, to route the circuits, or don't use poly as a conductor. It's not. It's a resistor. Okay, that's why whenever I want to introduce a signal into it, right after the gate, I'm putting a via here and drill a hole to the top and connect to metal 1 instead of using a long poly trace. Okay, one more question. Why I'm not putting this via directly on this trace? Why I have to introduce another wire here? It's going to be too close to this guy. Okay, and why I'm not moving this square a little bit to the more to the right, like reduce the gap here. Just move it to the right. So just eliminate this length. No. Keep in mind the fabrication resolution that even defines the corners here. You know what I mean? So if you tell them, if you move, for example, you move this poly 1 layer to here, okay, and you are basically creating a small gap, and the C5 probably won't be able to resolve it. It's going to report errors. Even in the same layer, like poly 1, poly 1, you still cannot keep them too close to each other, even though they are the same material, same layer, okay? There's a resolution issue. So sometimes, like something like this, in ideal case, you are seeing a really 90-degree right angle here, but in the fabrication, probably it's not won't be that sharp. It's rounded or something because of the resolution issue. Won't be that sharp. Same to this one. Okay, like the very top of the peak here or the corner here, probably is not a, just a 1 point. It's probably hundreds of atoms, stacking there. So it won't be a sharp corner there. Okay.
If it wasn't for the metal ones that would having the via in the middle of the poly
In where?
Like if these weren't here and you put this via just in the middle of the path of the poly, it would still work.
Yeah, it works okay. That's not a problem, but it just has metal 1 over here. That's why I cannot. Yeah, because the via is metal, right? And also you see this is the via, and the gray color, the gray area here is the red metal 1. That's how they made the little contact for you. It's something the library can directly use. You know what I mean? So it's for this thing. If you grab from the left-hand side of the library, it has a pink area which is a poly, and it has a via, and it has a metal 1. So the gray area is the metal 1. So if you draw a cross-sectional view of that via only, or that little contact only, remember you have a pink first, right? And then a gray square, and then a little dot in the middle. This is pink, and this is gray, and this is black. So how would you draw that cross-sectional view of it? You draw it. Box, poly, metal 1, come back here. Pink. Why do you need a pink area first? The poly, so you can connect the poly to it. Why do you have a metal 1? So you can connect the metal 1 to it. Why do you have a via? Yes. Make sense? So what are the layers here? So the bigger one is That's this guy. And what is this one? Yeah. What is this guy? Uh-huh. It's gonna be
Is there a
the,
reason that they need to be sized like that, or is it just to be able to see it on the 2 dimensions?
what did you mean?
Like, is there a reason that the poly is so much larger than the L1 node?
I don't know.
It's just so that it's easier to see.
It's probably just, the C5 or the 300 nanometer lambda rule defines it. They want to make the poly layer bigger than the metal layer, but it can make it the other way around. I don't think that's a problem at all. It happens all the time.
Yeah.
Yeah, see, metal one is this metal one is definitely bigger than this poly, right?
Right.
Yeah, not a big issue.
The smallest you can make those traces is lambda
Yeah, yeah, multiples of lambdas, I think. Mm-hmm. Make sense? And there's if the circuit becomes a little bit more complicated, you see like this one, for example. So during the layout, always try to get a via here first, as soon as possible. It's rule of thumb, okay? Don't, enjoy wiring, getting a pretty long poly layer all the time. So you can see in this layout, what I did was here, definitely you can move this closer to it. It won't be a problem, but this is pretty long, okay? And then I got a metal, the poly to metal one, and I got a metal one, okay? And what is this? Yes, a via, but this via is metal one to metal two. So the purple trace is metal two. Okay, so right after that, I got a via connect to metal two. So I'm actually routing the signals in the metal two layer. So it's better to have a type of trace, since you only have 3 metal layers, have one type of trace, like interconnect all the transistors or giving signals to it in a different metal layer, and all the metal traces inside the transistor to connect drains or something in the metal one layer, so it's easier to route signals. And there's another rule here which will make it easier to lay out your circuit, which is keep one metal layer vertically, like vertical traces, all the places, and metal two layer in the horizontal direction. You know what I mean? If you have metal one here and metal two here as well, for example, I don't have a metal two vertically. If I have a metal two here, I won't be able to use metal two connect the signal from here to here horizontally. You know what I mean? Just gonna short the metal two layer here. But this metal one is gonna be fine. They are running on different levels, different layers. So keep the vertical ones in one metal layer and another one in different metal layer. Okay.
When you're connecting the metal two to the poly, is it not possible to just put a via through the metal one layer instead of doing that, like jump down the metal one?
You can place 2 vias on top of each other actually, but it's not recommended. That's why what I did is like this. I don't know. I think people just didn't do that. It's probably more difficult to fabricate.
Is there an auto router software like this?
I think I did it very briefly once. It didn't work really well. So you have to go through this as a beginner. I think it's just something you need to know. And yeah. Oh, sure. It's definitely we auto route it. Electric VLSI definitely had it, but I don't know how to use it. It's just it's not really powerful. So what we did is in Cadence we auto route it's just one click actually. Yeah. Electric VLSI, yes, you can do it, but I just don't know how to do it. It's probably not as powerful as Cadence when you do the auto routing. I mean, you have like billions of transistors for the CPU Snapdragon. There's no way you can hand draw it. It's all auto routed. see. Again, so when you're drawing, make sure you, whenever you can, I just introduce the via and then use metal layer instead of keep using the poly. That's why you see these guys. I cannot put a via here because it's too close to the metal. Okay, have to turn it to the right a little bit so I can put a via here as soon as possible instead of using a lot of polysilicon materials. Make sense? See here, I need to connect this gate to this gate. So what I did here is, instead of directly using a poly layer to draw a trace, a pink trace, I did so many things to it. It's just one simple connection. And you can see I put the efforts in there to avoid using a lot of poly traces, right? So these two gates are connected. I introduce a via and connect to metal 1 and then metal 2. You can imagine how that works. It's like 2 poly to this, to this. That's how I connect them instead of using poly, right? That all makes sense? Okay. And there's a way that you can use poly, the polysilicon layer as a resistor, but with a lower resistance. So the way to do that is, here's a gate, for example, and that's N plus. So you can reduce the resistance of the contact and also the gate. You can deposit a layer on it. It's called silicide. I think the material is usually tungsten. To reduce the resistance of the poly layer. Okay. And for capacitors, I have an example here for you guys. If I want to design a poly to poly capacitor, so here's Fox. Here's the first insulation layer. And I got a poly 2, so the poly 2 is actually on the top of poly 1. The poly 1, that's P1, that's P2. Okay, and I got a metal 1, that's a via. Metal 1, and it's a via from poly 1 to metal 1. So it's going to form a cap. And when you design the cap, you can calculate the capacitance by using the given parameter of the one of the parameters in the process. So it's given. It's called Cox prime. It's a capacitance of the oxide layer because this is all the silicon dioxide, right? It's a dielectric material. So Cox prime equals, you can find this parameter in the textbook actually. So this one equals epsilon r times epsilon 0 over Tox. So Tox is also given. There's a thickness of the dielectric material in the middle. And this one, epsilon r, is the permittivity of a dielectric material. the electric material. And epsilon 0, you probably have seen this in a lot of places in physics. This is the permittivity of vacuum. This is the parameters that forms Cox prime. And so the real Cox, Cox equals Cox prime times A, which is overlapping area here, the area. So for example, there's a quick example in the textbook for the 50 nanometer technology. So the parameters can be found in the textbook in the table. And the overlap is 10 by 10 for P1 and P2, okay? 10 by 10 for P1 and P2. So 10 by 10 what? If I'm saying it's 10 by 10, means it's actually 50 nanometer times 10. It's a 10 by 10 square, okay? Overlap for the cap. So for that, it's going to be 50 nanometer times 10 times 50 nanometer times 10. That's the area of the overlap. All right. So what else do you need to find Cox? You need the capacitance. That's what you are designing for the circuit. You want to know the capacitance, which is actually Cox. Okay, you're calculating it, and this is the area, the physical area. 10 by 10 is just no units, just the 10 of the. It's not lambda, but it's the unit here. It's 10 of 50 times 10 of the 50 nanometer. It's going to be 500 nanometer times 500 nanometer for the area, overlapping area. What else do you need to find the Cox? And this is given by the technology, by the process. You can contact the foundry to find out that parameter, okay? And usually in femtofarad level. And this one, I think, is 25 femtofarad per micrometer square. So for the calculation in the future, this is going to be nanometer square, and this is a micrometer square. I have to find out the way to convert them into one unit, right? So Tox is the Cygnus here. No, yes, Cygnus. Mm-hmm. I will cover more tomorrow in the morning. So we'll have the lab in the 2771. A short lecture at the very beginning, okay? I just missed the ones for my whole